Word Problems Part 2 covers advanced statistics, probability, combinatorics, and overlapping sets. I'm Emily Sledge, and that is a lot to cover, so we're going to begin with a topic called interquartile range. This is a statistical measure about a set, and it overlaps quite a bit with the idea of median. In fact, we're going to take a median several times as we find the interquartile range. So the first step is to find the median of the overall set. And as you probably already know, to find the median, you order the set, or at least make sure the set given to you is already in order, as this one is from low to high. And then you find the middle term, which in a set like this one that has 9 terms is going to be the fifth term. 10 is the median of set S. Well, we're halfway to finding out the interquartile range. Put in other terms, the interquartile range is the range between quartiles. Which ones? Well, first let's define a quartile. A quartile is approximately a quarter of the data. So the median, sitting smack in the middle of this set, is the second quartile. Q2 equals 10 in this case. And Q1 is the first quartile. It's the median of the lower half of those data points. Notice that's in the middle of the lower half, which places it at, in 1/4 of the way into the set. Likewise, upper half, take the median there. That's the 75th percentile or the third quartile. So looking at it this way, the difference between the third quartile and the first quartile, it's like the half of the set that's in the middle. It's a snapshot of how spread out the set is. And I call it a snapshot because it's not as detailed a measure of the dispersion of a set, not the way standard deviation is. Standard deviation is calculated using information from each of the terms. When you take a median, you kind of ignore the terms, the highest and the lowest terms. You pick out the middle terms. So for example, if our last term, instead of being 22, if that had been 1,000,000, it wouldn't have affected the interquartile range in any way. All right, so just to look at this in a little bit more visual way, here we have the quartiles all given their own colors. So notice that each quartile has the same number of terms, and because this was a set with an odd number of terms, the median stands alone. And actually that idea of the median stands alone is one to take away from this. Do not include the median in either the upper half or the lower half. If you'd done that, you would have found different medians for the upper and lower half, and calculated the wrong interquartile range. So the message here is the median is not in either of the halves. It stands alone. So to put this into practice, here's one for you to answer on your own. Since this is a skill check question as opposed to an official question, I'm not going to put up a timer for this kind of problem during this lesson. I'll just ask you to pause the recording, work it out, and then come on back. Welcome back. And you may have noticed the big difference between this set and the previous set. This set has only 8 terms. That's an even number of terms. And so you know what to do. This one's already ordered from low to high. So as we find our median here, we have to take the average of the middle 2 terms. And that makes the median, or Q2, equal to -1.5. And that actually sort of takes care of one thing that we would have to normally think about, which is the median stands alone. So here the median isn't actually one of the terms in the set. So there's no way to accidentally include it in the upper or the lower half. So go ahead and include all the terms that are in the set as you think about those halves. And again, notice that each quartile has an equal number of terms in it. So Q1 again is the median of the lower half. Those 2 quartiles, first and second, each have 2 terms. There is no middle term of the lower half. You again have to take the average of -4 and -3. and similarly for the upper half. So when all is said and done, the interquartile range here is 4. All right, so that is interquartile range, a snapshot of the dispersion of a set. It tells you the range for the middle 50% of the data points. Another concept that you need to be familiar with on the GRE is also has something to do with the spread of a set, how data is distributed, and that's the normal distribution. Questions get asked about this because it is standard, and things that you need to know are that the middle in this case is the mean, and so that means the median is the mean here. In a normally distributed set, the mean equals the median. In other sets, that's not necessarily the case. Okay, so that's one of the things that makes this special and therefore question worthy. A normal distribution is also symmetrical about the mean, as you see here. You need to memorize these percents, but for the problems I'm about to put up, we're going to give you a little cheat sheet. I'll say a little bit more about the memorization piece in a minute. For now, feel free to use that cheat sheet. Take a look at these 3 questions. Again, just pause the recording as you think about them, and then come back for the solution. So we're given the median or mean weight of the weasels in this population, and we also are given the standard deviation. From those 2 things, you can know a lot about a normally distributed population. So the weight of a weasel 2 standard deviations above the mean, you would just take the mean weight and add 2 times the standard deviation and arrive at that particular weasel's weight. Within 1 standard deviation of the mean means from -1 on this chart to +1. 1 standard deviation either way, left and right, from the mean. And so add up 34% and 34%, and you get 68% in that range. That's the dark blue shaded area. Similarly, for the last question, add up everything from -2 to +2. And what that means is that within 2 standard deviations of the mean, 95% of the weasels are in that range. Another way to approach that is to look at just who's not included. 2.5% of the very low weight weasels are not included in that standard deviation range, and 2.5% at the top. So everything but 5% at the ends. And actually, I think this is the way to memorize this normal distribution. These are the 2 numbers you need to know, 68% and 95%. And just remember those as like who's included in 1 standard deviation from the mean and 2 standard deviations from the mean. When you go to 3 standard deviations from the mean, it's not technically 100%, but 100% is close enough. So most questions tend to ask about within 1 or 2 standard deviations of the mean. And notice that from 68 and 95, you can get all the other numbers in that chart, right? 68 cut in half is 34 and 34, and 95 minus 68 is 27. Split that in half, and you get 13.5% for these 2 areas. All right, so if you remember these and what they really mean, you'll be able to remember all the other numbers. I just want to show you this same kind of concept in QC format. So you may notice that, the same weasel population setup here, same mean, same standard deviation. And this is the idea that this can be phrased as a probability question. If you're randomly selecting a weasel, well, the normal distribution tells you the probability of getting a weasel is highest, that it'll be close to the mean, and less likely that you'll get a really, really heavy weasel or a really, really light weasel. Here they've given us a range from 4.8 to 7.2, and those are notable numbers because they're each 1 standard deviation from the mean. And we know from the chart on the previous slide 68% of weasels are in that range, so that's your chance of selecting a weasel with those weights, or within those weights. And the answer is A. All right, here's a QC question that I'm going to have you do on your own, and for which I will give you a timer on the screen. Probability question. Take 45 seconds on this one. Probability, fun topic because you can reason yourself into knots about what could happen. So one of the things about flipping a coin is that a fair coin always has the same chances, heads and tails equally likely, and that's not affected by how many times you flip that coin. It will stay fair. But on the other hand, if you're looking at what will happen over the course of all of those flips, the number of times you flip it does matter. So what am I saying by this? It's fair if you said, hey, there's a 1/2 probability of getting heads on each flip. It's just as likely to happen on the third flip as it is on the first. Absolutely true. But here we don't care about each flip individually. We care about the outcome of all three. Probability of 3 heads in a row. And I like to take certain probability scenarios and take them out to like an extreme because it kind of tests my practical experience with this kind of thing. And my practical experience is that if somebody flipped 100 heads in a row, right? They stood there and flipped a coin, it got a head every time. I would probably think that they were cheating. You know, the likelihood of flipping heads 100 times in a row is very unlikely. I mean, it's almost astronomically small probability. So that helps me realize that, okay, the probability of flipping 3 heads in a row has got to be less than the probability of just flipping heads once. Okay, just the intuition is that the more times you need to flip heads in a row, the harder it is to do. So the principle here in the actual math is that we want the probability of heads and then heads and then heads again. I'm emphasizing that word and because in math, probability questions, that means you multiply. So it's half as likely to flip heads twice in a row as it is to just flip heads once, and so on. So 1/8 compared to 1/6, 1/6 is the greater fraction. All right, here's another probability question for you to think about, again with multiple actions taken. So take a minute and I'll put the timer up for that. This number cube has an equal number of evens and odds, which means it's equally likely to roll an even as it is to roll an odd. And we'll use that idea as we think about the chance of rolling an even and then an odd. Notice the use of the word and in that question. Probability of an even and then an odd. So the and means multiply. And so the probability of even on the first roll is 1/2. Probability of an odd on the second is likewise 1/2. We multiply to get 1/4. And just to prove this another way, I like the idea of doing probability questions two ways until you build your intuition on these, kind of as a double check, and also just a way to get your head around what's really happening. You can think about the total number of possibilities versus the number of winning possibilities. So the total number of possible scenarios is there's 6 numbers possible on the first roll, 6 on the second. That's 36 total. And 9 of those scenarios are the ones that win, the ones where you get an even number first and an odd number second. I've written them out here, right? 2, 4, and 6 are your possibilities for the evens, and each of them can be paired with an odd number possibility for the second roll. Notice another key word in this question. It's not just asking us what's the chance of getting an even and an odd when you roll the die twice. It's specifying the order in which that must happen. And in general, the more restrictive or the more constrained the question is, the lower the probability will be. And so this constriction on order lowers the probability here. So notice that if it could just be an even and odd in an either order, those winning scenarios would double because we could just, look at the reverse order of each one of them. That would give you 18 winning scenarios out of 36 for a 1/2 chance. So the takeaway here is that the then is a really key number. Landing on an even and then an odd gives you a 1/4 probability. But if they just ask for even and odd in any order, the probability would be double that. So very tricky. Pay attention to the exact wording. You'll use that idea here. I'm going to put 1.5 minutes on the clock for this one. All right, selecting jelly beans from a bag. Lewis will reach into a bag that has 12 jelly beans in it. When we think about his chances of, or the probability that he pulls out a red jelly bean, on that first selection, the probability is 1/2. Half of the jelly beans are red, and we get that from 6/12. Now here's the twist in this question. At that point, the bag no longer has 12 jelly beans in it. He's taken that first jelly bean out, and we know this because they tell us he reaches in, gets the 2 jelly beans one after the other. So without replacing the first one, he selects the second. So that changes things. There's now only 11 jelly beans in the bag. And if the first was red, now there's only 5 red jelly beans. And if the first wasn't red, it's not one of our winning scenarios. So we're going to go down the winning path here. So probability that both of his jelly beans are red hinges on the first one being red. So what's the chance on the second one being red? Once you clear that hurdle, it's 5 out of 11. So the probability that both are red is 1/2 times 5/11ths, 5/22. So you'll employ this way of thinking on any question that has no replacement. So sometimes the wording of the question will specify, without replacement. But sometimes it can just be sort of implied by the story told, as it was here, selecting one and then another. And so this is the idea also of using things up or not. If you flip a coin, you don't use it up. Later flips all have the same chances that the initial flip did, if you're just looking at the individual flip. But in a jar kind of situation, you do kind of use up the quantity as you take jelly beans out. And that same principle applies if you're assigning people to a team. Once you've assigned them to the team, they're no longer to be available to be assigned again. All right, take a look at a probability question in QC format. Take a minute 15 on this one. So for quantity A, which has fewer restrictions than quantity B, it's a little more straightforward. We'll start there. Roll the die. What's the probability of rolling a 5? It's the same probability as rolling any other number. So each number is 1/6 likely, and that is quantity A. Now quantity B, you have to roll the die twice. And so 1/6 is your probability of any given number there on each roll. And whenever we roll twice, we end up multiplying. We've seen that before. And so it can be very tempting to just say, okay, 1/6 times 1/6. Watch out though. I find it's beneficial on probability questions to put it into words, even as you set up the math. Before you plug numbers into your mathematical equation, think about what that equation is with words in it. So what we're really going to do is find the probability of getting some number twice in a row. And mathematically, that's the probability of some number times the probability of some number again. And here's the kicker. On the first roll, the probability of some number is 100%. You're going to get a number. We don't care what number it is. What we care about is whether the second roll matches it. Isn't that interesting? So 6 out of 6 on the first times 1 out of 6 on the second equals 1/6. This is equal probability. because it's really only the second roll that can mess things up. Would be another way to look at that. Here's yet another way to look at that. 36 possible results, 6 on the first times 6 on the second. And if we list out our winning results, as long as the two rolls match, 1 and 1, 2 and 2, etc., we're good. And there's 6 ways that you can match. So 6 out of 36 is 1/6. All right, so the first roll, you're guaranteed. You'll get some number. We're going to switch gears with that one and move over to combinations, which sometimes overlaps with probability questions. And let's take a look at this warm-up. I'm not going to put a timer on the screen because I think it would block the work that you're doing. So please pause the recording and take the time you need with these 3 and come on back for the explanations. So Mark is making outfits, and he has 5 possible pairs of pants to wear, 4 shirts to wear. And bear in mind that he can combine any of those pants with any of those shirts. If he's wearing 1 pair of pants and 1 shirt, as we're told. And with all of those combos, he can pair up any of 3 hats. So as with probability questions, a lot of what you're going to do on combinatorics questions is multiply. When you're making combinations, every one of the 5 pant options can go with every one of the 4 shirt options. That's 20 combos already, and each of those could get a different hat. 3 hat options there, 60 total outfits. So notice that there's no restriction that he can't wear 1 certain pair of pants with certain other shirts. In real life, things might not match, but no restrictions here. Now, the second question is a question with a restriction. The parent must stand first in line. I've seen questions on standardized tests where the restriction is, it asks about ways people could sit in a car, but the restriction is that the driver has to be an adult. So that kind of problem definitely exists. If the parent must be first in line, well, there's no decision to be made there then. You're restricted totally. So really, the question of how many orders and can the 4 people stand really boils down to, in how many orders can the 3 children be ordered, since the parent has already sort of been spoken for. So here's a way to look at these questions. Placeholders, lines showing, place in line. The parent must be in the first place, so that is one possibility. You're restricted to that. Doesn't affect the math. And there's 3 children. If you line them up behind the parent, there's 3 possibilities for who could get in line first. But at that point, there's only 2 children remaining for us to order, 2 possibilities for who could get in line next, and then a decision has basically been made for us. For the third one, the remaining child gets in line. And so, total 6 ways. And you could even do this out in a brute force way if you wanted to convince yourself. Give the people names, P for parent, A, B, and C for the children, and write them out yourself. Write down the orders in which they could stand in line. You cannot come up with more than 6 ways if the parent must come first. All right, here we have a question about passcodes. 3 digits, can't begin with 0. Okay, so you can't have like 027. We are talking true 3-digit numbers. And that's actually the best way to look at this one, I think. 3-digit numbers end at 999. And we know that there's 999 numbers between 1 and 999, right? They sort of count themselves. But we know that we need to exclude those numbers that are like 3-digit numbers that begin with a 0. 001 through 099. And we know there are 99 numbers in that range. And so the 3-digit numbers that are valid are just the difference there. 999 minus 99. Another way to do that is with that placeholder method. So here we have placeholders for hundreds, tenths, and units digits. And notice that the tens and the units digit have 10 possibilities. They can be 0 through 9. But since the first number cannot be a 0, the options for the hundreds place is 1 through 9. That's 9 possibilities, just another way to get to 900. Here's a combinations problem. I'll put 2 minutes on the timer for this one. Imagining yourself as the coach of this basketball team is one way to approach this problem. You're a coach, you have 5 slots to fill, and think about making the selection of each player for each slot. So put that on your paper, literally with the slots. 9 players are available to fill the first slot, but once that player is selected without replacement, again, you have 8 possibilities for the second player you're going to select, only 7 for the third, and so on. And you're selecting each player and then the next player and then the next player. So and means multiply. And we end up with a number of teams that's too large. It's 5 times the highest choice or the greatest choice. So we know that there's something we've overlooked here. And this is the issue in combinations questions. Does order matter or does it not? Another way of thinking about order, because it's not always order, is, is there anything different about these players or isn't there? They don't really tell us these basketball players are different from one another. I mean, they're different individuals, but, is it any different to be the 5th person picked on this team as opposed to being the first person picked to be on the team? Well, from the perspective of the players, no, they're all on the team. We're not told they play different positions, for example. So the problem with this method is that it has counted team A, B, C, D, E as one team, and it's also counted every other way of ordering those people as if they are different teams. But in this particular scenario, these same 5 people, in any order the coach picked them, would be the same team. And so this question boils down to how many times did we overcount this team? And that's another way of asking that is how many ways could you shuffle these people? Each of those ways got counted. And that is 120. There's 5 times 4 times 3 times 2 times 1 ways of ordering those 5 people, assuming they're the ones that you selected. So 120 is the factor by which we overcounted. Divide Divide the number we know is too big by 120, and you get 126. Okay, so this method is realistic. You're imagining what you would actually do with the selection of these players. But it leaves a lot to chance, in my opinion. You have to really think to yourself, do I need to divide here or do I not need to divide here? A method that's a little bit more automatic is called the anagram grid. So notice that factorials have a lot in common with what we're doing there. 9 times 8 times 7 times 6 times 5. That's part of a factorial. So if we know that we're going to be using factorial numbers, the anagram grid sort of automates what goes in the formula. So we've got in our grid 9 placeholders for the 9 people, and A through I are just sort of placeholder names. You don't even have to name the people. What really matters is the bottom part of the grid, where you capture what's happening in the story. So I find it's useful to think, is there anything different about these people? It is different to be on the team versus off the team. But for the players on the team, there's not really anything different about them that we're told. So give them the same letter in your anagram word. So we've given all the players on the team a yes, all the players off the team. Likewise, there's no difference among them. They're all just off the team. Give them a no or an N. And here's where things get automatic. The anagram grid just tells you what goes in the denominator of the formula. The top of the formula is always going to be a factorial with the number of available players in this case, or the pool from which you have to choose. So 9 factorial, the total group goes on top. And all the action in these problems really happens in the denominator, what goes there. And so every letter that you have will yield a factorial in the denominator, and the number that goes with that factorial is how many of that letter you have. So there's 5 Y's and 4 N's. There we go. Just another way to get there. And I just wanted to look here at a variation on that question. So if instead of just talking about selecting basketball players, it had said selecting a team of 5 basketball players to play 5 different positions, one each of forward, guard, dribbler, shooter, and bouncer. Now, I know that those are not actual basketball positions, so don't write in. I'm just being silly. But I'm being silly in a way that lets us look at how the anagram grid would differ. So in this case, it is different to be the forward as opposed to the dribbler. And in your anagram word, give those different letters. So here they're all 5 different letters. So how does that affect the formula? Well, you still have 4 factorial for the 4 people who are not on the team, but each of those positions is now just on its own. Each letter gets a factorial with the number 1 factorial. So notice that what this formula always has is you should always have numbers down here that would add up to 9, right? We have 5 1s and 1 4. And this basically just tells you that you've accounted for everybody. And actually, you may recognize this math. This is the math we did initially when we just thought about selecting 5 people to be on the team. So this shows how the answer could be 15,120. All the players would have to be different. Order would have to matter. All right, here's a combinations question in QC format. So take a minute 15. right, so we are selecting a delegation of 5 people, but it's not that simple. Those 5 people have to meet these criteria: 1 sophomore, 2 juniors, and 2 seniors. And so it's not one big pool of people and just 5 people chosen from it. There's some restrictions on the class, and there's different availability among the classes here. So the anagram word, or at least the concept behind it, will help us set this one up. So if we look at the number of delegations possible, we want to know just the ways to combine sophomores and the juniors that we have to pick and the seniors into one delegation. So those are in the brackets there. First is sophomores. Let's take a look at that expression. So there's 7 sophomores. That's our pool to choose from when selecting sophomores. 7 factorial is on the top of the fraction. And we're going to select 1 sophomore and leave 6 people out. So that's 1 yes and 6 no's. 1 factorial, 6 factorial in the bottom. And that same idea we're going to use with the juniors. So there's 5 juniors available, and we have to select 2 to be on the conference. Now, they don't say that one of the juniors is first junior delegate and the other is second junior delegate. And there's no difference. The order doesn't matter among the 2 that are selected. They just go with the committee. But that leaves 3 behind. So 2 factorial, 3 factorial is in the denominator there. Likewise, for the seniors, 4 to choose from, you're going to choose 2, leave 2 behind. And you can clean those up. One of the nice things about factorials is all the canceling that you can do. So, for example, in the second brackets here, 5 factorial is 5 times 4 times 3 times 2 times 1, but 3 times 2 times 1 gets canceled with this factorial, leaving 5 times 4 and the other factorial number. So always cancel in factorials with your biggest factorial in the denominator. Go ahead and just cancel that out. And also notice that when we do that with the 7 factorial here, 6 factorial wipes everything else out of that. So it cancels, and this leaves us with just a 7 possible options for the sophomore that we choose. And that makes sense, right? If you're choosing one person from among 7, there's 7 possibilities. So the factorial form was a little bit overkill for the sophomores, but it definitely was worth doing for the juniors and the seniors. And actually look at it in this form. If you wanted to shortcut and skip over the factorials, even for the juniors and seniors, you could do kind of a slot method. Think about selecting a junior. There's 5 to choose from initially, and then for the second selection, there's 4, and then you divide by 2 to account for the fact that order doesn't matter. All right, so you could have gone right to this step also. Do out the math, you end up with 420. A is the answer. This is a combinations question in a fill in the blank format. For these, you have a standard 2 minutes. I'll put 2 minutes on the timer. So looking at three-digit integers that begin with 4, 7, or 9. All right, that's the 400s, the 700s, and the 900s. And I think that's probably the easiest place to start. It's kind of practical, right? 400 all the way to up to 499. That is 100 integers. So one way to see that is take the highest minus the lowest and then add 1 before you're done to account for the fact that you are including 400 in that count. Look at the 700s, much the same thing. This just shows another way of kind of thinking about how many terms that actually is. We know that's 99 of them from 701, 702, 703, up to 799. That's clearly 99 of them, kind of counting themselves. At plus 1 for the 0th, the 700 number. Again, 100 integers in that range too. So by similar logic, there's 100 that start with a 9 as well. Okay, so that's a total of 300 three-digit integers. And if you answered 300, you did what I did, which was overlook something very important. We don't care about all of the 300-digit integers. We care about the even ones. So half of these are even and half are odd. 150 is the correct answer. So even restricts the numbers that we're looking for, three-digit restricts the numbers that we're looking for, and those beginning numbers restrict what we're looking for. An alternate way to approach this, kind of an approach that we've used before, and that is, put slots down for the digits. In the hundreds place, we're told it has to begin with a 4, 7, or 9. That's 3 options. The middle digit can be any single digit number from 0 through 9. That's 10 possibilities. And for this to be an even integer, it has to end in 0, 2, 4, 6, 8. That's 5 possibilities. And the product there is 150. So arguably that's a little bit more direct than just kind of counting the integers. Plus I think it's a little easier to keep the even restriction in mind if you have to think about the possibilities for each digit individually. All right, switching gears to overlapping set questions. I'll give you 2 minutes to think through this one using any methods that you know, and in the next few questions, we'll cover a few different ways of dealing with these kinds of questions. Take 2 minutes. The patients in this study all experienced nausea or headaches. And some unlucky patients experienced both. All right, so whenever you see words about some people experience one thing or have one thing, and others fit in a different category, they have or experience a different thing, and also, especially if you see the word both, you're probably dealing with an overlapping sets question. So one way to set these up is with the Venn diagram. So you've got one circle to include all of the people who have nausea, and one circle for the headaches. So on GRE questions tends to be only two categories, with kind of the third subcategory being the people in the overlap. And that's where you should begin these questions. They're all about who's in the overlap. So always label, if you can, those in the both area first. So we know that 40 patients have both nausea and headaches. That 40 is in both circles. And we start there because overall there are 52 patients who have nausea, but that includes the 40 that we've just placed already in the nausea circle. So before you put a number down, you've got to back out the people who have both. So the people who have nausea but don't have headaches too are only the 12 remaining. Likewise, the 40 comes out of the 66 who experience headaches, so only 26 experience headaches but not nausea. And we're told that nobody has neither symptom. So everybody inside either of these circles, that accounts for the entire study patients, the entirety of that group. All of them experience nausea or headache, and so our total number of patients is 12 plus 40 plus 26. 78 is our answer. An alternative way to deal with these problems is more of a formula, but the formula, if you already know this formula, this is probably the method that you'd want to stick with. If you're just learning the formula, I think it's great to learn the formula, but also the Venn diagram, because the Venn really explains why the formula is what it is. So the formula is always, one category plus the other category minus those in both categories plus those in neither. So here our categories are nausea, headaches, minus both plus neither. And here neither is 0 because everybody had a symptom. And you can see that that theme of backing the 40 out so that it doesn't get double counted appears in this formula as well. All right, I just want to quickly show a variation on this problem to show what would happen if there were some people in the neither category. I think that the neither possibility is kind of the drawback to the Venn diagram. If you have neither symptom, you're outside both of the circles, and it's easy to forget about those folks. So one way I think to keep them in mind is to draw a universe around your Venn diagram. So you have not only the people, so your universe contains not only the people that have the symptoms, but also the possibility of people who have neither. And just place those inside the box, but outside the circles. And the same kind of idea would apply. You'd still label both first in your Venn diagram, back that out of either of the distinct categories. So notice too, this is important to note, 52 experienced nausea. You can double check that within the nausea circle, there are 12 plus 40. And the same for headaches. 40 plus 26 is the total of 66 that have headaches. Occasionally, you could see a question where in the words of the problem, it specifies, hey, this is the number that goes right here, and there's no need to back out how many the people in the both categories. So for example, if the problem had told us 26 patients experience headaches but not nausea, well, then we would have just dropped to 26 in here. No need to subtract 40 from that. And again, the formula would have worked on this problem. 88 is our answer here. We still have the same number of people with the symptoms. The only thing that really changed was the 10 that had no symptoms. All right, try this out yourself. Students at a school, take 2 minutes. So this is an overlapping set problem because they talk about an entire group of students, but specific students are mentioned in 2 categories, algebra and Spanish. And they also talk about both algebra and Spanish, so that's a clue that overlap is possible between the 2 sets. So you could set up your Venn diagram, label the circles algebra and Spanish, and account for that overlap of both. And our possible numbers there are our 5 choices. And you always start with the both number if you can. So that suggests that we might want to set up that Venn diagram, drop in these various numbers in the both category and see what happens. That could be time consuming, though, to kind of do trial and error of 5 different Venn setups. So don't overlook common sense. Sometimes a little bit of investigation will show you a shortcut. If 0 take both, then the total number of students is at least those that take algebra and those that take Spanish. And that's 407, that's too many. We know the school has fewer students than that. So in other words, if there's no overlap, we have too many students, and if we have to have 400 students, there must be some students that take both algebra and Spanish. Likewise, at the high end, you can't have 157 students taking both algebra and Spanish when only 156 students take Spanish. So, of course, 251 is ruled out for the same reason. And luckily, this question tells you 2 answers are possible. The 2 that remain must be correct. So I think setting up the Venn diagram and dropping 0 in the middle might have helped see that whole thing about the total being 407. So that could be a good place to start. But then look at your answers and see if there's going to be any others that show similar funny results. This brings us to optional and advanced problems. So if you are pressed for time and need to get to your homework, you should leave the recording here and go ahead and do your work and come on back and watch the tail end of optional and advanced problems later if you have time then. But if you have time now, continue with us. We have a few more problems that we can take a look at. Here's a challenge problem on overlapping sets. Take 2 minutes. You can definitely do this problem with a Venn diagram. I will show that, but I think the better way to go is the formula approach. The format of the choices really looks like the formula. So that might be a hint here. So the formula again is that the total should be one category plus the other minus both plus neither. So here the two categories mentioned are computer science and management. And we have values for the various items. So CS gets replaced with X in the formula. Total gets replaced with 200. Management gets replaced with Y. Just be really careful about what's what. So that's why I like to write out the general formula and then sub in. Both is what we're looking for, so let's just keep that in the formula, and neither was P. So at this point you are halfway there. All you have to do is solve this for both, and you end up with A. So it looks like the formula because that's what we started with. So here's that same problem with the Venn diagram. CS and management are your circles. Put B, a variable, as your both. Start with that, and then you have to subtract both from the total X in computer science to get computer science people who are not management. That's X minus B here. Likewise, with the total for management being Y, that means Y minus B is the amount to put here. So notice that the sum in this circle is Y. This is a bit overkill because what we're going to end up doing is adding these all back together to add up to the total. And notice that neither category in the universe outside the circles. And pretty much you end up with a line in your calculation that looks like one of the lines above, and it's the same from there on out. So, you could argue that setting up the Venn diagram isn't really necessary. Gets you to the same place, but takes more steps. All right, here's a probability question, QC, so I'll give you a minute 15. This question introduces the relationship between an event occurring and not occurring, or the probabilities that an event will occur or not occur. Well, those are the only two possibilities. It'll either happen or not. And so the total of those probabilities must be 1. We use that idea in quantity A. For both quantities, we're looking at the probability that two things will happen, this and that. So and means multiply. But in A, it's the probability that A will happen times the probability that B will not happen. So here's where we use that 1 minus the probability that B will happen is equivalent to the probability of B not happening. Okay, so we now have two quantities set up as mathematical formulas. And you might cancel. You might say, okay, the probability of A is the same in both of these. We're really comparing the probability that B will happen to the probability that B will not happen. Or you could just plug some numbers in. So if the probability of each of these things is 0.5, we are told that events A and B have equal probabilities of occurring, then both the quantities are 0.25. And if you picked C, it's likely that you stopped there. But if this was the only case you tested, it's likely that you were making an assumption based on the language at the top here. Events A and B have equal probability of occurring. That means they have the same probability as each other, but there's nothing in this statement that says they are the total of all possibilities, right? If events A and B could each occur and they account for all possibilities, and they're equally likely, well then 0.5 must equal 0.5. They must each be half likely to happen, or have half probability. But it's possible that neither event happens, right? They may not account for all the possibilities. So in other words, the probability of event A happening could be 0.1, and B could have probability of 0.1, right? They don't have to add to 1. And if that's the case, then you can show that quantity A is greater. The probabilities of each could be 0.9, and the balance would shift again. So the answer is actually D here. There are cases where they're equal, cases where A is greater, cases where B is greater. Probability question. Multiple choice, so I'll give you 2 minutes. Before thinking about possible rolls of the dice, it might make sense to look at what it would take to get two numbers that multiply to an even number. And for that, we go back to odd and even rules. Okay, so you can get even by doing even times even. You can also do even times odd in either order, right? We are rolling these die in order. So if an even comes first or an even comes second, it doesn't matter. You still get an even product. Really, there's only one way to get an odd product, and that is if both of the numbers are odd. So in questions like this, where there's lots of ways to win, lots of different ways to get a winning scenario, it's often simpler to look at the ways to lose. There's only one way to lose here, and that is if you get to roll two odds. So let's look at the probability of that happening. What's the chance of not getting an even product? Well, you'd have to roll an odd, which is 3 out of 6 is your probability, and you'd have to roll another odd, 3 out of 6 probability. Multiply those together because of and the chance of getting an odd product is 1/4. So the probability of getting an even product is 1 minus that. Okay, so the takeaway here is sometimes the 1 minus x trick. If the probability that you're looking for is kind of complicated, but the probability of losing is simple, figure that out and back it out of 1. All right, this is the last one in the set. It is a probability question, and it has cookies in it. So take 2 minutes. So this is indeed a probability question, as the heading suggests. Probability is the main word in the question. Probability of a person selecting one cookie, the probability they will get a cookie with chocolate chips, nuts, or both. It's a pretty complicated scenario. So so you could get chocolate chips alone, nuts alone, or a cookie with both of them. That suggests that maybe the 1 minus x trick would be useful here. You know, what's the probability of getting a cookie with none of those things? Okay, so that's one idea. This is also an overlapping sets question. How do we know? Talking about cookies, and 2 categories are mentioned: chocolate chips, nuts, and overlap is mentioned. You can have a cookie with both. So for this last question, I wanted to introduce just a different, yet another way to deal with overlapping set questions. and it's the double set matrix. You can use this any place where you would use the Venn diagram, a two-circle Venn diagram. There are, by the way, 3 circled Venn diagrams. You could have a third category. If you see a question that has 3 categories, you must use the circles because you can't draw a 3-dimensional chart. But if it's only 2 categories, as most of these questions are, you could set it up this way. And the idea behind the setup is that one category goes in the columns and one category goes in the rows. You're putting columns that are, you're labeling your columns with things that are categories that are opposites. So it is the opposite of having chocolate chips to have no chocolate chips. It is the opposite of having nuts to have no nuts. Chocolate chips is not the opposite of nuts. Okay, so don't put them next to each other in either columns or rows. Another way to make sure that you're labeling the rows as mutually exclusive things or opposites is to phrase it as a question. So you might write nuts, question mark, yes, no, would be your row labels. If you can put a yes and a no there, you know they're opposites. And the big thing that I think the Venn diagram has going for it, the double set matrix has going for it that the Venn diagram does not, is a place to keep track of a total. You know, in the Venn diagram, you have to look in all the little sections of the circle and set up a formula for your total. But this gives us a place to not only capture the grand total of 48 cookies, but also capture some subtotals too. Here's the total of all the cookies that have nuts. You'd add across, get the subtotal of all the nut cookies, and all the nut cookies added to all of the no nut cookies would give you the grand total. So this is the way the chart works. It adds across, and it also should add up down. Subtotals in all of these places. So let's work our way through the given information. We already have captured that 48 cookies are there. So moving left to right through the text, go clause by clause. Don't try to deal with more than one thing at a time. So 3/4 of those 48 cookies have chocolate chips. All right, so the grand total or the subtotal of all the cookies with chocolate chips is 3/4 of the grand total. 36 cookies have chocolate chips. That is 3/4 of all the cookies. And that implies that 1/4 of the cookies have no chocolate chips. Okay, the other 12 go here. And notice that this checks out. 36 and 12 must add up to 48. Next piece of information, half of the cookies that have chocolate chips also have nuts. Very important to note the language. When you're taking a fraction of something, pay special attention to what follows the of. That's what you're going to take the fraction out of. Don't go on autopilot and just take a fraction of the total again. Half of 48 would be a mistake. Half of the cookies that have chocolate chips are these. Half of these cookies. So half of the 36 cookies that have chocolate chips would be 18. Those 18 have nuts. And that implies that half don't have nuts, right? So 18 being here means 18 must be here in order to get a total of 36. Boy, we're getting somewhere with this. So the next piece of information is that 2/3 of the cookies that do not have chocolate chips, again, it's not just 2/3 of the cookies, it's 2/3 of the certain cookies that do not have chocolate chips. So 2/3 of these 12 that do not have chocolate chips do not have 2/3 of the cookies that do not have chocolate chips are these 12. 2/3 of these 12 have nuts. They do have nuts. So 8 goes here, 4 goes here. Notice how useful it was to look at that information in pieces. Very easy to reverse these two, right? No chocolate chips, but they do have nuts. So with that, we can turn our attention to the question. We're looking at chocolate chips, nuts, or both. So if we aren't going to use the 1 minus x trick, just circle those. The ones that have both chocolate chips and nuts, are these. The ones that have nuts alone are here. The ones that have chocolate chips only are here. The total of those is 44. So a person has a chance of getting one of those. That's 44 out of the total of 48, which reduces to 1 over 12. 1 minus x trick might have been easier here. There is a 4 out of 48 chance, or a 1/12 chance, that a person would select a cookie with neither nuts nor chocolate chips, plain cookie. And so you could subtract that and get 11/12 that way. That's our last problem. Good luck with the homework.